it's my pleasure to introduce Dr. Rob Ambrose as the RI seminar speaker. So it's a big milestone for me because some of you thinking Rob Ambrose, famous NASA robotics. No, this is the first time I've got to introduce someone who's retired. Dr. Ambrose is Carol Ambrose's husband, is that correct? Kathy, excuse me, that wasn't correct. Kathy Ambrose's husband. And he worked at I guess, NASA, Johnson Space Institute for about 21 years, 2000 and 2021. But a long time ago, and they don't say it in his bio, by the way, when these dates happened, he got an undergraduate master's degree at the University of Washington in St. Louis. And then obtained a PhD in Texas, where he now works at UT Austin. So they did give PhDs back for quite some time. But I think he's best known for, I think he's best known for his service to our country in working in NASA, also serving as an advisory role at NASA as well. But I think we robotics geeks kind of think of him as the guy who built Robotics. And the younger robotics geeks may have heard something called Valkyrie, which is sort of like Robonaut, but newer. But he's known for being one of the skilled mechanical engineers in the robotics field. And when we find these rare artists almost who are mechanical engineers, you just gotta sit and listen to these guys talk about whatever they want because it'll be a great learning experience. So with that, I'm gonna also point out that Rob, Dr. Ambrose, is shamelessly looking for people to recruit from here to Texas. And all of you can go, but after you graduate, if we don't offer you a job after you graduate. So with that, I give you Dr. Ambrose.
I may have told Howie my most important title is Kathy's husband, and all the other titles are secondary. Pleasure to see you guys. I haven't been actually here in a while, but I used to come every now and then, and I always enjoyed my time here as one of the great places in robotics on Earth. I'm going to talk to you about maybe just a romp through a bunch of the robots that I worked on at NASA, and then show you some of the new stuff. I'm working at Texas A&M, and you know, as Howie said, I was at the Johnson Space Center as the chief of the software robotics simulation division at a headquarters for a while. But before that, I worked for a little company, a little startup company, back before that was cool. You know, back then it was only scary. And I worked for an FFRDC called MITRE. And traveling today with a bunch of friends from A&M. Dr. Gray Thomas is our most recent hire in the robotics area, postdoc at Michigan, and his PhD from UT Austin. And we've got Daniel, Vitter, Magali, Sarah, and Rishi all here today. We've had a fun tour of your lab, so thank you. All right, so that's JSC. That's where I worked for many years. That's supposedly Clear Lake in the background. It's really a bayou, not really clear. And I was responsible, my offices were in like Building 9 complex and a few of the other buildings. So what I'm going to do is I'm going to romp through a bunch of robots, and I'm going to have to do it fast because I'll spend too much time on these if I don't. And in each one, it was a problem that needed to be solved. So the robot was designed to solve a problem. So I always like to start with that. And so in each one of these, I'll describe the problem we're trying to solve. The first was the Robonaut 1 system, and the problem was everything on the outside of the spacecraft was built for gloved hands, and those are incredibly expensive, like $500,000 an hour. And it'd be nice if we could have some robotic hands out there. And there's no way we could go back and redesign everything on the outside of the spacecraft, since most of it was already built. So the Discover Channel, they heard this idea, and so they made this animation on their own. We didn't tell them anything. They just did this on their own. And it was kind of a concept of this thing that would climb around on the outside of a spacecraft. And there are all these knobs and levers and latches and terrible electrical connectors that you would never want anyone to have to use. But it's all built for gloved hands. And so this was before space station had even been built. You're climbing around, patching holes, I guess. It takes as much as 6 hours to get out to patch a hole. So the idea that the robot's already out there was kind of a good idea. So let me show you now. This is a video of me when I was a lot younger and a lot lighter, and back when my beard was red-ish. And I'm going to show you me working with a guy named Fred, who happens to be inside this robot named Robonaut 1A. And this robot's now in the Smithsonian. Fred now works at Honeybee. And we're going to do a four-handed task. So we're going to solder two wires together. So you have to hold one wire with one hand, you have to hold the other wire with the other hand, you have to hold the soldering iron, and you have to hold the solder, right? So 4 hands. And look how I talk to Fred, and we'll see if there's audio. We'll see if there's audio. But you're going to see down in the corner, you'll see one of Fred's eyes that he can see out of. And watch how I kind of point at things, and it's just like I'm working with Fred. But you'll also hear Fred, if the audio works, you can hear Fred talk to himself. So he's talking to his robot body and telling the robot like to freeze different limbs and thaw different limbs, and then the robot's talking back to Fred. So it's kind of an interesting conversation between me, Fred, and Fred's robot body. So let's see if the audio works.
We're going to start off by soldering these two wires together, okay? Take this wire in your left hand. Bring it back hand. Right arm movement. Take this wire in your right. Right hand. Right hand movement. Put those together while I get the soldering iron and the solder. Very nice. You got it. I'll put it back, please. Draw right hand. Right hand off. Okay. Very nicely done.
So that was very deep telepresence. Fred was immersed, VR helmet, gloves, body tracker, but there were key autonomies running that made that possible. First of all, you should not stand next to a robot that's that strong without some key kind of like force control reflexes built in for safety. But there were also some force controllers running that allowed Fred not to be perfect. And when you're in deep telepresence, it's very hard to be perfect. So not ripping the wires apart, it was all about some force controllers. And we tried a few other things. This was Dr. Bill Bluthman kind of bossing the robot around. We tried gestures, we tried voice commands, and we tried just pushing. And the job they were trying to do was, Bill was trying to feed the end of that stick into a socket. And so that's a two-person task typically. One person's the master, and the other is kind of the apprentice. So the boss, the more experienced person, is in the front, and the apprentice is in the back, kind of just doing the simpler job, guiding the back end of the stick. And what we found was, of the three, force was the best. That if you were that apprentice person, and the boss was kind of moving the stick around, you would feel it and just kind of go with the flow. And it turns out that was the most effective of the different control modes that we tried. Here was an example. This was like one of the hardest things people have ever done in space. This was the servicing mission for the Hubble Space Telescope, and they had to get this door open, which was the easy part, and then they had to pull out some boxes, and then they had to close the door, which was the hard part. So we had Mike Massimino, who was the astronaut who had just done this mission, and Dr. Nancy Curry, who I have the pleasure of working with at A&M as one of our faculty. They kind of coached Fred through the teleoperation of this. For example, Mike said, look, count that hole, and you'll be watching that hole. And Nancy was the one who actually counted, because they were kind of a team. Mike was on the end of the robot that Nancy was driving, so the two of them were kind of working together. And Massimino said, once you get that socket in there, go ahead and use it as the tool, because you've already got it on the head of the bolt, and you can't get your gloved finger in there. So he said he just kind of used the tool to kind of fish the bolt out of the slot, and turns out that actually worked pretty well. So he said, that boy said, don't get off, just kind of fish it out of there. And you really don't want to get your finger caught, and you don't want to get your wrist around that pit pin. And he said the problem with the pit pin, when you have to pull it out of here, there's a ball detent, and there's two plates, and there's no way to get it perfectly aligned, and you can't see it, and your head's in the wrong spot. So Massimino said the most important thing is you got to jiggle it. And so Fred jiggled it and was able to get it through there. And then there were a bunch of other steps, and it was a really complicated task. What we found was with full immersion and some force controllers that were protecting the robot from an imprecise human teleoperator, we could do some pretty good things. But we very quickly, in the Robonaut program, went into more autonomy. And I believe in both. I love the idea of immersing a person where they're, and ignore the fact that it's on wheels, that was another story altogether. But the idea that there's a person with judgment, but then there are force controllers that are other autonomies that are managing. I really like that combination. All right, moving on. So that was in the late 90s. So all that vision work, force control, late 90s, early 2000s. Then changing subject completely. Inspection. Totally different morphology of robot. So this was a free-flying spacecraft that we launched out of the shuttle, kind of like a Falcon. And it was being operated with a very low level of autonomy. It had hover and a few other basics. But the pilots were inside the shuttle, and everybody was amazed how steady the video was. It wasn't blowing in the wind. It was rock solid. It's like, well, of course, what else could it be? And it was basically a foam-covered ball. We called it air cam. All right, then we went back and built another Robonaut 1. I was the only one who called it Robonaut 1, and then I was the only one who called it Robonaut 1A. We built 1B, where it was completely portable. And actually, this is Dr. Nancy Curry, my friend, is an astronaut. So she was doing a task that had been done in the shuttle with 2 astronauts, and we showed that Nancy could do it with her and 2 robots, and could build this truss as fast as 2 astronauts could. And it, kind of weird, but this is floating on air-bearing floor. That's a worksite interface fixture. We did some early climbing. This was about the time you guys built Skyworker. Remember that? We were talking about climbing on the outside of spacecraft, and it's something that I'm now coming back to later in my career, and I think it's cool. Then switch gears again. Okay, air cams, better air cam, smaller air cam, more autonomous air cam, using GPS and a few other key features, much smaller. Then switching back, another robot. We decided to start, since Robonaut 1B was portable, it was a torso, we could start putting it on lower bodies. And this was the dumbest of the lower bodies. This one was the dumbest, dangerous, most ridiculous thing I probably did in my career. But DARPA gave out 25 of these and said, see what you can do with it. And I put a multi-million-dollar robot on it, and it was stupid. Very, very wobbly and dangerous. And but the idea was to be able to have mobile dexterity, to be able to not have to have work come to you, but to be able to go to the work. And that mobility and manipulation together is so important. Here's an example. And I was probably standing off to the side going, oh my God, I can't watch this because it's just so dangerous. Look at the mode of vibration in there. It's just really dangerous. And we had quite a blooper reel from the 25 ones that were given out, a lot of injuries actually. But here, we told them, go over there and cut the blue wire. And then at the last minute, I said, oh no, red wire. Okay, cut the red wire. And I think that was Mike Goza doing it at the time. But just being able to roll over to something and fish out a wire and cut it, that normally takes a lot of time. But I don't recommend this. 2 wheels is crazy. So then we started trying around other lower bodies. So this was probably the most extreme lower body we built for the Robonaut series. See that circle at the end? That's where a Robonaut goes. But the real job of this was being able to assemble very large structures, like large solar arrays, like acres of solar array. And the idea is the spider would climb carrying panels on its belly out and then kind of squat and install them. And what climbs best on a gossamer structure? A spider. The idea was if humans climb, humans put very large torques on the structure. So a spider can climb with its 8 legs and only put pure forces, no moments, onto the structure. So you could, for 10,000 pounds of structure, you could make it over an acre rather than a relatively small area that's very stout. A spider would be able to climb, and this robot was able to climb with about a 1/4 pound of force on each of its footfalls. And here it was on an air-bearing sled, so the only forces were actually due to propulsive inertia loads on the legs. Actually, Carnegie Mellon was on this team. There's a guy, Fred Hager, doing a PhD. Yeah, he was a student named Fred. It might have been Sanjeev Singh's student. He was doing some of the coordination. There was Brett Kennedy's lemur. We had another couple other robots in there, and the CMU software was like sequencing between the different robots. All right, this was one of the other robots. This was a borescope, this we called Tendril. The mission at that time was to be able to go into a small hole like we had gotten on the shuttle Carbon. It's a robotic borescope. It was 1 centimeter in diameter, and it had 6 degrees of freedom and about a meter of propulsion that could go in. Then we tried another lower body for Robonaut, and this time again, mobile dexterity, much better. 4 wheels, much better. Very stable. Put a lot of time and effort into what we call the mid-body, and I spent thinking about how to put arms on rovers. Everybody puts them on the very top and then they could barely reach the ground, right? That's not the way to put it. There's a picture of one that I did with you guys where we mounted one of the Robonaut 1 kind of commercial variant arms down low on a chassis so that when it could reach the ground, and it had dexterous workspace intersecting with the ground, and that's really what you need. So with putting Robonaut 1 on this, we built a mid-body that would be able to bend the whole body down, and my dexterity analysis said that if I can put the elbow on it, that's in the dexterous workspace of the object. So being able to bend that down, remember back in the day when we had SICK lasers, remember those giant cinder blocks? Being able to get down low, work, and then it could spin around. See, it had a little workbench on the back of the robot. It was a workbench. It had tools, holders, and it could set stuff. Robots don't normally have pockets, so it's really awkward. Once they pick something up, they have no place to put it. So having a little workbench on the back of the robot was kind of cool. And then we did this multi-robot sequence where we had all these different kinds of robots. This was the beginning of what was called the Human Robotic Systems team. We had big robots for moving modules, and we had little rovers and human scale rovers, and it was a lot of fun thinking about different kinds of robots and how they could all work together. Then we decided, okay, that rover, I really need to go after something better. So rather than just copying the lunar rover, all that I had learned in designing manipulators, I decided I'm gonna go build rovers. That's what I want to do. And so I got into some pretty hardcore rover design. And let me show you a couple of videos. So this one, start with just the active suspension. So each leg on this machine has 3 degrees of freedom. So it has an active suspension up and down. It has independent steering that's not coupled to any of the other legs. And then it's got drive. And with those 3 degrees of freedom in each of the legs, no matter how many legs it has, we have the ability to do a lot of things with the torso, the body of this rover. So we can move the body up and down, which most rovers can't do, and we can pitch, and we can roll. And that allowed us to go dock with tools, pick tools up. If anybody's used a bobcat with like the quick attach, we could go dock with bulldozer blades and excavators, and that became really important. In this video is, it's got a sequence in here, we call it the Ode to Crusher. Crusher was this incredible Carnegie Mellon robot, but so much less power than Crusher. This is running on an electric battery. But you see here, it doesn't really have any forward. So as it's driving, the kinematics of this chassis are such that there's really no front. And with the active suspension, you see it's just kind of this, like an animal going over the terrain. It's got this, look at that clean belly. There's just nothing, no suspension arms sticking out, no oil pan, no differential, just clean. And we found also the asymmetry, driving 2x3 versus 3x2. It can pitch differently than it would roll. We learned a lot about this chassis, and all rovers that came came from the Chariot design. And that's actually the flag that's in my office now. When I retired, they gave me that flag. That pole came from the Apollo era. That was pulled out of the archives, the poles on the moon. They made some extras, and but they weren't designed to take wind, so they got bent a lot. Now check this out. Here's Crusher, the Crusher, Ode to Crusher, going right into a vertical wall and just, oh yeah. Go right up that. That's just, when I saw Crusher do that for the first time, I said, that's the way to do it. So that was with active suspension. This next one, we're going to zoom in. It's not going to use active suspension. It's just going to do it the way Crusher did, which was put so much forward drawbar force that you could drive straight up a wall. And I mean, that's Crusher, man. And I love that machine. All right. Then we started putting cabins and other things on this chassis. So that's the same chassis with a pressurized cabin. So this really changed the way we thought about rovers and people on the moon. The unpressurized rover, where you've got to wear a suit, the suit just beats you up. It's just really hard on you. So the idea of basically building a low altitude spacecraft where you could move around in a more comfortable environment and then pick your spot, decide where you're going to go, do your EVA. And then we had these things called suit ports. So the suits are already outside, so you could go do the EVA very quickly and get out. And instead of taking 6 hours to go through a pre-breathe and an airlock, the suit's already outside. And we also found that we had a bunch of geologists, and they found that they could do pretty good work, not in a suit, just relaxed, looking through low windows. And the suit's pretty challenging. Now these are low fidelity suits. These only weigh like 90 pounds. The real suit weighs 350 pounds. But you basically climb through double hatches into them and separate. And that's my friend Mike Gernhardt and a Smithsonian geologist who was on the team. Those two guys lived in that rover for 2 weeks, nonstop. And there was a myth that that's impossible. No, people could not live in a rover that small for 2 weeks. Now the Gemini capsule was only 2.8 cubic meters of volume, and we made 2 astronauts live in that for 2 weeks, and they came out mad, really mad. These 2 guys came out after 2 weeks pretty happy, but they had almost 11 cubic meters. Plus they were getting out, and it was just much better. And this machine, now all thinking about long-term exploration on the surface involves pressurized rovers because of this series of prototypes. All right, then we went back to the Robonaut series. This was a great partnership with General Motors, and it was predicated on the idea that we wanted the dexterity and the manipulation of a strong enough robot to be, a reasonable member of the team, but it had to be safe enough to be right next to you. So this machine is like an NBA power forward, big reach, strong, 20-pound force in any direction at full extremis. Did a big sweep there. Now it's going to do that same motion, and a person's going to get in the way, and it's going to be okay because we developed and patented the first rotary series elastic actuator, and we have the patent on it, which was a very simple spring design that we were able to put in series with the actuator, and this was around 2006 when we invented that. I've been working with my friends at MIT. All of their series elasticity was just beautiful, but it involved all these pulleys and strings and linear sensors, and I wanted a simple, if I could just put one part on the end of an actuator and get series elasticity out of it, that's what I wanted, and we were able to do that. So this was a critical advancement in what's now thought of as cobotics, and Dr. Gray Thomas, who's with me, has all sorts of new ideas on how to come up with the next generation of these springs, and I'm really excited to see where we might go with that. All right, then of course we started building lower bodies for the Robonaut 2 class, and this was a major upgrade. So this chassis now has the same kinematics as that Chariot, but it's only 4 legs, not 6 legs. Each leg only has a single wheel. So we're playing with parameters in rovers, and on one end of it you could put a Robonaut, on the other end of it you could put a bulldozer blade, which is a really good combination. So a humanoid has a lot of finesse, but it's not going to be super robust, and you're not going to dig with it. You would never use a Robonaut class manipulator with a shovel to dig. That'd be dumb, right? So what you would rather have, on one end, it's got this really cool bulldozer blade we developed with Rob Mueller at Kennedy, and on the other end, a dexterous humanoid. This was being commanded across 10 seconds of round trip time delay. Very high level of automation. We would designate the rock, the robot would feel it. All our work with GM was completely autonomous because it didn't make sense for them to have a teleoperated robot. So it would designate, it would feel, it would put the palm on it, it would grasp it, it would pull it up. And because it's a government robot, we would tell it wrong rock, but it didn't mind it because it was a robot. And then we would move on to other rocks. Let me see if I've got a video of the dozer. The dozer was pretty awesome. So this was some of our early work thinking about darkness and trying to operate. This was like around 2011, 2010. So I think we took the Robonut off so it only had the dozer blade. And you'll see some of the beautiful dexterity of the chassis and how that can couple with the dozer. So if anyone's driven a Bobcat, you're gonna wish you could drive a Bobcat like this thing drives. So very interesting bucket that could rotate all the way through. But now watch how this thing can, what we call it a swerve drive. It can turn on a dime, of course, but it can blend between that kind of a mode and being able to basically designate any point. In this case, we're designating the end effector as the point of resolution, and we could pivot around that point. Just incredible kinematics in the chassis that really work well with a bulldozer blade, especially a dump system like that. Okay, I'm gonna keep going. So then one of the things that we saw when we were working with Robonaut was they kept giving us jobs on the assembly line that were hurting workers. And at one point I said, well, it would be so cool if I could just take the Robonaut hand on a stick, and then I could just grab stuff like a hockey stick, right? I could put some buttons. That's right, I'll have a Robonaut on a hockey stick. And then I'm not gonna get carpal tunnel. I could reach all the way into the car body and do stuff. And then we started thinking about that, and well, no, that's dumb. How about if we just put it in a glove? How about if we just put my hand on the Robonaut hand, and then it does all the, no stick, just put it right on my hand, and then it holds the object, so its tendons are taut, my tendons are relaxed, and now I don't get carpal tunnel. So that was really the idea here, and what it got us to, after 2 or 3 generations, we then integrated it into the Phase 6 astronaut glove. And that's like 5 levels of fabric, and we've taken the outer garment off. We were doing, this is in a glove box at pressure. We were doing, delta P pressure across the glove. The glove just propels your fingers open. And to hold something, it's like an isometric exercise, and then the air propels your fingers back. So what I really want is just power steering. And this wasn't quite there, but this was grasp. You'd touch something and it would grasp it. And that's not a bad start. But where I would really like to go in the future with more wearable system is more just like power steering for a pressurized spacesuit. All right, so then we built a couple of these, and having 2 of these, this is the way. I mean, if you have 2 rovers like this and you're cruising around on the moon, I mean, you own the moon, right? And you want 2. You really want 2 because there's a crater out there somewhere that's going to swallow your rover no matter what you do, right? So you really want 2, and they could dock hatches and we could transfer astronauts. So we did a field test with 2 astronauts in each for 2 weeks, and they all came out happy. We had 2 men and 2 women. It was awesome, and these were just kind of showing off videos. But it was mainly they were being run by a science team out basically exploring this area of geology in northern Arizona. And there were a bunch of geologists who knew all the answers, like they'd done their PhD on which layer of lava had flowed first. And then the science team didn't know that. All they had was orbital data. And so they were trying to figure out what were the right orders of the lava flow. And they were running the astronauts around, taking samples, trying to identify all the contact lines. And, but we had a little bit of fun with it too. And I think this video shows the most dangerous thing we ever did with the rovers. Anybody read the book The Martian? Where in the book he flips the rover. So look how, these are super fines. This is a square-edged quarry, and the fines have blown up, and it's really super soft. And he went way into that, and rumor has it we had to change the seat cover on the seat, but he got through there. Look how deep into that stuff he went. And what's really weird is the other guy then followed him. I don't know. Okay. All right, so then we took one of the Robonauts, actually the one that I'd given GM. I said, I need that back. And I built them in some more later, but we took Robonaut 2B apart and rebuilt it, and we had to swap out all the power electronics that didn't pass radiation, and we took it to the International Space Station. And so here's some videos. Again, very high level of autonomy. We call this supervised autonomy, where we're telling it, flip that switch. And flipping that switch that it's doing right now, that's like the worst switch. You got to open the lid. That little shiny, slippery piece of sparkly, hard to see chrome. What a horrible switch. But all we would do is say, flip the switch into the on position, and then it would do that. And then this busy board had all the horrible interfaces that are built for these amazing athletes called humans. You know, buttons and latches, and these you have to pull the thing out and then move the switch over. I mean, who would build a switch like that? But it had knobs and latches and Velcro and levers. And I mean, if you could have the world rebuilt so that I could use a simpler robot, do it. But the world's, built, but it's coming. Where you can have a simple robot that does like one job really well, like a Roomba, I'm all for it. And you see in the mix of robots, I've got a lot of single-purpose robots, like free-flying inspection robots. But if you've got a complete wide open set of every possible thing that could go wrong in a spacecraft that just happens to be built for people, I don't see an easy solution. We played around with the legs. These are very creepy. These are designed to climb in zero gravity, so now we're getting back to climbing in zero G. They do not look like human legs. Astronauts climb with their hands, and their legs are just kind of like trailing. They don't have prehensile monkey feet, but why not? So we said, okay, we're going to build, these are really I call them pedipulators. They're really manipulators, and the end effectors are designed to grab seat track. You could take one of these off and put a hand, so you could have four hands if you wanted. You could put 4 hands, but I thought 2 general hands and 2 very specialized feet would be a really nice combination. And at this point, we also really upped our game on the force torque control. But you notice the whole arm is soft and padded, so even if it doesn't have the series elasticity, it's still not going to hurt you. Look how smooth it is. There's no cable harness coming off of it. There's no sharp edges. So just right off the bat, this thing is going to be safe around people. There are no pinch points. There are no weird offset joints, and that's hard to do. Making an arm svelte like that takes a lot of mechanical design work. And then all the soft goods, pushing a hole through the middle of the whole thing so there's no cable harness. But check this out. That is a light touch. And in zero gravity, wow, it was fine. And look at that. We call that the Gumby mode. Those big gearheads, takes a lot of force to backdrive them, but he was backdriving them with his fingertips because of the impedance controllers that we had in the system. All right, I'm going to keep going. Jetpack. That's fun to build. It's basically the same propulsion system that we had in that AirCam free flyer. It's got just enough in case you fall off the spacecraft to pull out the joystick, turn it on, you hit a button and it detumbles you, but you might be looking at the wrong direction. So in our VR lab, we would train the crew on how to fall off the spacecraft, detumble, point, stop falling away, aim at the airlock, go to the airlock, and leave enough in the tank so when you get to the airlock, you can stop. It was really important to have a little bit left in the tank so you could stick the landing when you got back to the airlock. More wearable stuff. This was a spin-off of the Robonaut 2 series, where we took all that technology, we built a really nice lower body exoskeleton, working with my friends at IHMC. You know, they built this exoskeleton, and this young lady is walking for the first time, and she's crying, and I'm looking at the exoskeleton, and that's making me cry. I said, we could do better than that. So we basically took all the Robonaut joints and we cut them in half, and we repackaged it in a really sleek design that allowed you to put it on while sitting in a wheelchair. You know, what's the point if it takes 3 people to get you in the exoskeleton, right? So we made it so sleek that you could put it on while sitting in the chair, and look how thin those are. And then that ended up being the femur of the Valkyrie later, which was great, and the shoes were also part of our work. Built another batch, gave one back to GM like I had promised. They're all over the place now. We sent them into other labs. There's one in Australia even. Howie, you were talking about pipes. This was a robot we built, and I actually sent my engineers on an offshore rig in the North Sea. They wanted to go down into this massive cavern and see what was growing in there. And so they had this pipe, and I just seen a bunch of femoral artery surgery, and I said, hey, does this cavern have a pipe, like an femoral artery? And sure enough, it did. And so it had this massive pump. And so the way they would do it, these cisterns at the bottom of the sea, they would pump oil into them all day long, and then when the ship would come up, they would pump seawater in, and it would push the oil into the ship. So they're giant storage tanks. And so I asked, hey, if we could design this thing that we put into the pipe, we could turn that pump on and it would flush it in there rather than trying to build something. And so my engineers, who apparently have the authority to have a personality and a sense of humor, they named it the teleoperated underwater robotic device that could be flushed into the tank, non-official name. And then it had different things. It could take samples. The first one it got into, it didn't look anything like that. It was all gopped up with wax, and crustaceans were living in there. And the bowling ball with the giant 10,000 horsepower pump cleaned the pipe out. That was probably the most valuable thing the robot did, was push the gunk out of the pipe, and then we could retrieve it back. And see how it's oily. Really good graphics work. Then Red, you got to drive this, right? So, and I'm going to quote you. So Red said, I've driven a vehicle with every one of the control modes this vehicle has, but I've never driven a vehicle with all these control modes. You could switch between each of them. This thing was awesome. It basically had all that kinematics that we'd been exploring with the other rovers, but it could do like 20, 35 miles an hour, and it was a lot of fun to drive. So it could do diamond, point turn, swerve drive, crab drive. You could put it into Chevy mode where it would just drive like a car, which is just sad if you make it drive like a car. And so we did this for a automobile company who'll go nameless. That wanted the idea. So what you could do with the kinematics of this is you could couple 2 of them together. If you hook 2 cars together with Ackerman steering, they can't steer, right? If you hook them back to back, they can barely steer. But if you hook these 2 together, they could steer just as well as, you could hook n number of them together. So with these kinematics, it allowed you to put them together and combine, and see how it's about half the length of a car? That's kind of nice. All right, I'm going to press, Howie mentioned Valkyrie. Here's a evolution of Valkyrie learning to walk. So the thigh, based on that X1 exoskeleton, just an interesting, this was baby's first steps. Very tentative, very hard to watch. We were working with IHMC and Boston Dynamics, so the same software that was being developed concurrently on a much higher, like 30 kilowatt Atlas, hydraulic Atlas. We're trying to use it on a 3 kilowatt Valkyrie. Same hardware, a little more confident walking. It's going with its dynamics. It's counting on being able to take a step. It's no longer statically walking. We evolved through 2 or 3 different approaches. using much more upper body, more aware of its CG. Did a lot of treadmill work, poor robot. We've now built like 5 or 6 of these, and they're on 3 continents right now. Again, same hardware, just better software algorithms, evolving. Same bus voltage, nothing got faster, just the software's a little more confident. And that's the key to this is hardware availability for your software team. If your robot's always broken, the software team just can't get going, right? So constantly giving them time on the chassis. We put them out to 3 different universities where all the universities could be working on them, and that is a great model where they all had the same chassis. And Valkyrie broke down into 6 Pelican cases, very modular, and when they would break a piece, they would ship it to me, and I would ship them another part. Then I'd refurb it, and so by the time we were done, the MIT robot had the hand from Northwestern or Northeastern, and a leg from Edinburgh, and we just were refurbing them. All right, some pretty high level of autonomy. So autonomously, we would give it where we wanted it to go, and it would autonomously map out all the footfalls using its LiDAR, and you see kind of the mind's eye up in the upper left, identifying safe footfalls and coming up with its plan. And it didn't always make the same choice I would have made, but it had a very high probability of getting there. And again, give your software team as much access to the hardware as you can. A software team needs to be hardware rich. All right, then totally different thing, we built another, this is an exercise device. For some reason I was responsible for exercise equipment on station. And we basically took a Robonaut hip joint and we built the world's most awesome rowing machine. It was really pretty awesome. Then back to rovers. So this was the only project in the entire portfolio at NASA focused on the lunar surface from 2013 to 2015, and then probably into 2018, because they're talking about going to the moon. There just weren't any real programs. And this was, back then it was called the Resource Prospector mission. Again, same kinematics of those other rovers, but watch what we can do with it. So I'm going to play this video. You recognize that lander? It's awesome. This is the way to build a lander. If you're going to put a rover on the moon, that's the way to do it. Most of the landers have something so high up on them. I mean, look how low that thing was. It's awesome. All right, so I'm going to play this video. The rover's going to drive across this super soft soil. It's going to get stuck, and this is at 64 times speed. But watch what it's going to do to get unstuck. So each of those legs has suspension, steering, and drive. We've not added any other things, but we've just played around with the offsets. The offsets in that wheel, very important, and the speed and the gate, and basically allowed it to unstuck itself, which is critical for the moon. I was also responsible for the daily operations on space station. This is like a 2-month sequence of manipulations on the space station. Now, there wasn't an inspection camera, so that's all CGI. But this is 2 months in the life of the robots on the International Space Station. They unloaded some spare parts out of the SpaceX Dragon trunk. Incredible machinations because of the kinematics of the robot. The robot's having to constantly pick things up and set things down because it doesn't have pockets. It's going to end over end. So the arm, the shoulder becomes the wrist becomes the shoulder. There it's unloading some spare parts. It's going to put them all out. Once it gets all these pieces, it's going to then try and take them out to a work site. Puts it all on on these attachment points on the rail. Steps onto the rail, steps off, and then rolls down the rail with all of its stuff. And now it's going to start picking all those pieces up and load them into the spot where the spare parts were needed. An incredible number of steps because of the number of limbs. The fact that the same robot chain has to flip over again means it has to set everything down before it can reconfigure itself. And that means it takes 37 hours to change a light bulb. Literally. It takes 37 runtime hours to swap out a bad modular unit with a new modular unit. 37 hours to change the light bulb. All right, I'm going to skip that. Skip that. Now, that resource prospector evolved into the Viper rover. Here it was coming off of an astrobotic ramp. You know, we're pretty sure there's not going to be some 4x4s sitting, but those are like emulating a 20 centimeter rut row. Here we're going to see the next evolution of that swimming gate. This is they call this the sink tank. That everybody else that would go in there was just down. You know, when people would walk in there, they would compress the soil. They're walking on like 1 inch of soil when they would walk in there because they would just crush it. Then we have to refluff it for the testing. And here was, I think this was first drive off. So Astrobotics moved their lander mock-up to JSC, and this was the first time we practiced driving off of the rails. And my goal was that it was going to be like a rack and pinion, that the wheels would just be designed for the rack perfectly, right? I mean, why not? It's the only engineered surface the rover will ever drive on the moon. And so I wanted it to be very clear that the guy who designed that wheel had seen that ramp, and the guy who designed that ramp had seen that wheel. You know, and often in space, you look at two things coming together where you think, I don't think those two guys ever saw each other's stuff, right? But we spent a lot of time on that, and that was important. So that would allow us to achieve really high, you know, steep ramp angles. All right, let me try and get wrapped up here. All right, so I retired 2021. Very proud of what I did at NASA. I love NASA. But I told the A&M folks, I got some robots I still need to build. And I'm spending a lot of time on time cards. I'd like to get back, get my hands dirty. So A&M is just an incredible organization. 74,000 students. 24,000 of them are engineering students. A decade ago, that was 12,000. We doubled the number of engineering students in the last decade. We have 15 engineering departments. And then there are all these other campuses. It's an amazing place, and it's mainly the attitude of anything I tell them. They say, well, okay, how much is that going to cost? Let's go do that. It's an incredible attitude. So on the west side of campus, there's this old, it used to be the Riverside campus. It was an old World War II airfield, 2,000 acres. And we've owned it since, I guess it was decommissioned after the Korean War. Buzz Aldrin and Gus Grissom were test pilots, flight teachers out here. And we just had Buzz was just there last week. We put a statue up for him. So 2,000 acres, we've set aside a autonomous proving ground for our work with the Army robotics. We've got an off-road area. We're building a bunch of other stuff for hypersonics. This proving ground, all engineered surfaces, fording trough, rumble strips. The Army is bringing robots to us to do kind of shootouts and evaluations. We've also got this Research Integration Center, which is where my main labs are. And it's brand new. It opened the week I got there. It's my new Building 9, like I had at the Johnson Space Center, and I'm really excited about it. So I'm working on 4 projects I want to talk to you about just briefly. And the problems, these are the problems I'm going after. The first one is getting into a really deep, dark crater. And then some dual spacecraft and manipulation and some logistics handling. So let's talk about the crater. So that's Shackleton. You know, it's about the size of the city of Houston. You know, it's miles deep, billion years old. We're not going to send astronauts in there anytime soon. So my thought many years ago, like 20 years ago, was what would get to the bottom of that crater quickly? I mean, you got 10, 20 centimeters a second. It's going to take a long time to go to the bottom of that crater, and it's 40 Kelvin, and they're probably going to be frozen by the time they do. Viper can only do about 6 hours in a crater like that. So how about a ball? I think a ball will get to the bottom of that. So here's the robot that me and some guys built 20 years ago. That's Lyndon Bridgewater. He's now the chief engineer on Viper. This is when Lyndon, I think that's me, about 30 pounds ago. Lyndon's now, at this time, Lyndon was a senior at U of H. This was his senior design project. So it's a ball. It's a 40-inch ball, and it's kind of out of control. But I said, there's something about this. How do you think that moves? You think there's a gerbil in there? Definitely a robot gerbil, right? There's, but look at that thing. And I said, I'm going to stick a pin in there. I'm going to come back to that robot someday. And so now is that day. So the idea is this soft robot. This is ball B2. So this is second generation. We built a 2-foot version of it. It's a little wobbly, but it's doing better. We're working it. We got a great IMU in there. And again, the team's getting lots of time on this ball. I'm confident we're going to get the controls to de-wobble this thing. And then it's a soft, pneumatically controlled ball that can air up and air down. And son of a gun, it can drive on water. And I've been thinking for 20 years what it would look like to drive this on water. And we have this fording tank out at the proving ground. And without any extra tread or anything, we just drove it down and just motored around in there like it was born. And it's not on the ground. That's floating. And with a little bit of tread work, I think this thing's going to be a real aquatic winner. So what could it do? Well, here's how it works. There's a pendulum inside. In this case, it's in training wheels. See how the pendulum's leaning backwards? That's how it works. So across those two gold hubcaps is an axle, and the pendulum lifts, causing the ball to roll forward, and it can lean left and right to steer, which means it really has very few moving parts. And you could just throw buckets of sand at that. It has no orifices. It has no seals. It's a ball. It's a beach ball. I dare you to have a beach ball be afraid of the beach. It's just not going to be afraid. It was born to be on the beach. It's very impervious to the environments. It's purged with a gas. All the electronics can be lovingly warmed in a gas inside it. And I think it can make it to the bottom of a big crater. And but what would it do if it got there? So the deck size that we're building is a 6-foot ball, which in Texas we refer to as a medium. And it has a 6-inch pipe for the axle, which can hold 16U cubes. So you have 16U worth of payload that you could carry to the bottom of a big crater. Or you could put one big 16U payload in there. And what I would really like is a rocket that leans over, gets a sample, and fires the sample out of the crater. So if the crew could just get this thing up to the lip and roll it in, it'll make it wait. It's going to find something deep. It might get trapped in a local minima, the size of CMU, right? I mean, it's such a huge crater, right? It could get maybe trapped, and take a sample and fire it out. We'll figure it out later. But we're not going to send people into something like that. So that's the problem I want to solve there. We also have a problem. We don't have a U.S. vended manipulator, so I'm all over this. And I don't want to say too much about it, but I've been building robot arms for a long time. This is going to be like my 4th or 5th generation. And I'm working with the Johnson Space Center on applying some of the technologies of a reimbursable Space Act with them. And I want to apply the Viper technologies. That's TRL-6, about to be TRL-7. I think I can give us a really good U.S. vended manipulator. And a bunch of companies are have already talked to me about wanting to license it. This one's fun. Anybody seen one of these before? This is a palletized loading system. It's a 56,000-pound truck, and it's designed to pick up and set down shipping containers. But it takes multiple people to do it. Look at that. It's 10-wheel drive, going up pretty rough slopes. This is out at our proving ground. Look at all the engineered slopes we've got. This is a great place. If you want to come test a robot, bring it. We're set up. But it's got this big arm that can reach out and grab a shipping container and pick it up and put it back on its back. And so a lot of people have built the autonomy for platooning these and driving these, but no one's gone after the arm for reaching out and grabbing the container and putting it up and down. And so we're gonna go after that. And then lastly, This is our new dual spacecraft simulator. This is shot from yesterday. So these just got installed. So on one side, it's a Stewart platform with a 7th axis that's infinite rotation. And on the other side, it's a 24-foot rail with a Stewart platform. So I'll be able to emulate 2 spacecraft in contact with each other. So I can do dual spacecraft operations. And I've actually worked on a proposal with Howie where we might use such a, calling it the Robotics Space Simulator, where we might try some new ideas we have. So those are some of the problems I'm going after. I also have an opportunity that I just want to share with you. The state has set aside $350 million for a new commission. Of that, they've directly appropriated $200 million to me and my friend Nancy Curry. We're going to build a new building. And the Johnson Space Center has all this land on the west side. They've put it up for lease. And I said, I'll take some. And I turned in a proposal for 32 acres. And I'm going to build a heck of a facility right there. And what we're going after is a place to do lunar surface and Mars surface engineering, science, operations, and workforce development. So here's some recent architects' renderings. A 4-acre indoor air-conditioned lunar yard and a 4-acre indoor air-conditioned Mars yard. Now, at JSC, I owned the JSC Rock Yard, and it was horrible. Of all the months I spent, mostly, for some reason, August. It was always August. And there were no restrooms, and it was just horrible. And by the time the robots would get out there, they would be glistening because it would be so humid, they would just rain on them. And this will be a much better place for the people and the robots, but we'll also be able to completely darken this out. So here's our place to have total control of lighting, put a Mongo lamp over in the corner, and let's do some really high fidelity driving training for our crew, training for them just walking in terrible lighting. There's basically an oval track that's I'm using to drive the design. It's the classic Olympic 400-meter track. And so we'll be able to, one of the key questions we're going to answer is how far can an astronaut run in a suit if they really, really, really have to, or else they're dead? How far can they run in a 350-pound spacesuit in 1.6G? We're going to answer it right there. But all the other things with the rovers and climbing up and down ladders and setting up experiments, this is the place we're going to do it. And down the center, between these 2 giant buildings, is kind of the building for the people. And on the ground floor of it, we're not calling them labs, we're calling them garages. So you'll have a garage, which kind of looks like a lab, but it's a garage because when you open the roll-up door, you roll out onto the moon or to Mars. So these garages are going to be available for researchers to come use. So if you have like an experiment you want to do on the moon, we're going to have a place for you to go set it up and do it. And then on the upper floors, we'll have some overlook rooms. It'll be like control rooms where you could run a simulation. And if you like it that much, you might then actually run your thing from once you get it working with your practice, you might just want to stay there and run your real mission. So we're really excited about this. The money's already in the accounts, working with the architects. We're hoping for opening day, August 2025. So a little bit less than a 2-year build. And then let's look at the garages. We'll have 10 double garages or 20 single garages that will allow you to just roll out onto a lunar or Martian surface. All right, so yes, we're hiring. Shameless slide, I apologize, but I'm just starting, building up a team. We're looking for grad students. We're looking for research engineers at all levels, so bachelor's, master's, PhD. We've hired them in all levels. And we've got a tenure track, open rank, so assistant professor, associate professor, full professor, if you're interested. We're hiring, and would love to have colleagues from Carnegie Mellon somewhere in the A&M DNA. I think that would be really good. So with that, I just want to say thank you, and the name of our lab is we're the Robotics and Automation Design Lab. So we're We're the rad lab. Dave?
So I just noticed for the first time that the chassis for your spider robot bears a lot of similarity to the chariot chassis.
It's exactly the same.
Okay.
Good eye.
My question-
Except for one thing. The spider had 8 legs and 3 body segments. Chariot had 6 legs and only 2 body segments. But the whole brainstem, avionics, where the batteries were, it was the immediate robot built after the spider. And I don't think we built that chariot chassis in 11 months. We were told to go, and we rolled out of Building 9 in 11 months with that big chassis. It was because we had just built Spidernaut and used the same batteries, same computers, same cable harness technology, and all the guts that are all the most important parts. And then it allowed us to go fast. And throughout all those robots, there was this chronology of taking ideas from one and moving them into the next. And it's nice to have a diversity of manipulation and mobility and wearables, and to have that mixture. Really, I benefited over my career from getting the privilege of being able to work in each of those. It's kind of in parallel. Other thoughts?
The ball, does it were you inflating it once it's at the bottom of the crater or
No.
from the beginning?
Yeah, so the way it works is you charge it with a certain amount of air, and inside the ball is a compressor and some tanks. And when you turn the compressor on, it deflates the ball, taking the air from the ball and putting it into the tanks at a higher pressure. And then you vent the tanks to reinflate the ball. So it's kind of like in a submarine with ballast, but you charge it with a certain amount of air. And right now the 2-foot ball, it can go from 2 psi to 4 psi.
So you just choose one,
Yeah.
whatever inflation.
Well, so we charge it, and then it can do plus or minus 1 psi with the pneumatic system. But it's the pneumatic tire is this amazing thing, and it's basically a spherical tire. And we're starting to do experiments on traction, and all the Becker equations, they all assume a cylindrical tire. So Magali has been looking at how to rewrite the Becker equations for a spherical tire, and then get traction as a function of pressure on that circular patch. That's one of the things we're working on. Yes, Heather.
What's your difference in pressure from Shackleton Rim to the bottom of the crater?
Well,
With that difference in temperature.
So another thing is PV equals nRT, and what we want is it just to be hot. We want that ball just to be hot. So as it's going down, it's a generator. We're going to get to the bottom, and the batteries are going to be charged, right? So we probably want to go into the crater half charged, so we have some capacity to absorb, regen all that. But we need it to be hot because I can't find a material that's flexible enough at cryogenic temperatures to do this ball justice. So what I want is an outer rind that has a low conductivity, and then just some really hot gas that's keeping that ball hot. And it really can't stop. It needs to be a rolling stone, to stay hot and get to the bottom. But it's a one-way ticket. It's not coming. It's going to go until it pops or plops. But yeah, you can do the PV equals nRT, being able to control gas pressure. But the real thing is, what is the gas? And I'm thinking argon, which is a lunar element. We think Viper's going to see water and argon as the top 2 volatiles. And we can't use nitrogen because it'll condense, right? So we've got to have something that will not condense even as it starts to get cold.
So this sort of, it almost answers the question, or it gives me an assumption, but one of the things you were showing was it going on water itself as well.
Yeah.
Do you see future uses of it on a Titan mission, things like that, where they're still looking at how do you do over and under ice and things like that? You just said with the cold it would be problematic, but... Yeah,
so these are short-lived robots, right? But this thing's going to do great on methane, you know, and what you don't want in a methane world is any open orifices to electronics. I mean, you want the whole thing bagged, and so a ball would be, I hadn't even thought about tightening it, but yeah, a ball would be great to keep all the electronics away from methane. But it turns out on Earth, there's a really good application. And if anybody's worked with the military, there's something called a wet gap crossing. A little rough, like one of the most dangerous things. So, and just 6 inches in diameter, 64-inch long payload bay. So, if anybody's got a cylindrical payload, it would probably fit well in that. So wet gap crossing. It could also just drive off a ship onto shore, right? And so we've got a beach field test in our future where we're going to the beach. You know, think about robots going in and out of the surf. That's a horrible thing for a robot. Most robots should never go near surf. I mean, going in and out of salt water and sand, that's horrible. Almost every robot I've ever built would immediately be destroyed going anywhere near surf, but it's a beach ball, and it's going to be just fine. So driving in and out of the surf, you know, hovercraft, maybe, but you know, this is a ground robot that could drive in and out of surf, could drive off of a ship's deck onto an island and hop between islands. So, Howie?
So I have two questions. One's about the ball. So how do you, I guess, have a vision system or a sensor that can detect its surroundings?
Yeah, it's tough. Radar's awesome.
So will pass through
Oh
material?
yeah. Radar's really good, but we're going to have to put something on those hubcaps besides just an A&M logo. There's going to have to be something there. And like, remember Sanjeev Singh's camera that had the parabolic thing? Imagine a horizontal one of those that would just see everything. Yeah, that would be my favorite camera as a fisheye, and then you would only sector. You wouldn't spin it. You would just digitally spin it. Only look at the sector that you would want. So, but yeah, you know, it's such a simple thing. There's just no place to put a lot of stuff, right? But
My second question. So throughout your whole talk, I was looking at all these cool robots that you were building, and I thought to myself, God, that's complicated. Those are complex.
well, the ball has 3 parts.
Except for the ball. So maybe you're short-circuiting my question, and is the answer just build balls?
Well, our motto for that project is be the ball,
Be the ball.
and just try and keep it simple. And I don't know that we are keeping it simple, but you know, it's a different thing, right? And you know, when was the last time you saw a ball driving around, right? And they're out there. So we've found some really terrible ways to build balls. I'm sorry, we found other options for how to build a ball. We found all flywheels inside. We found just a tumbleweed where the wind blows it wherever it wants. I'm not sure about that, but I saw one at IROS where sticks come out. They're like 20 sticks that all poke out and push the ball, kind of commutating. There's the little thing that's inside the ball that's driving, like the Sphero toy that you can buy. It has 2 drive wheels and then 2 passive wheels that push up and press the drive wheels. It's just driving on the inside of a ball, right? I mean, there are different kind of morphologies of the ball, but I think the pendulum, so that 2-foot ball, 25-mile-an-hour top speed.
The point I was trying to make is those rovers that you build, I feel like there must be some struggle between functionality, actually, excuse me, I misspoke, robustness and complexity of the design.
Yes.
Because you want to be able to build as simple a robot as possible to go to the moon and light as possible. And all
So here's the thing. There's nothing simple about getting on a rocket and blasting to the moon. Most of the failure modes are softly landing on the moon, or else everybody would be landing softly on the moon right now. We have a lot of robots driving around, but softly landing on the moon is not done every week. And so I think that's the risk. And we looked at Viper. We looked at all of, because there was Ames brought in a group of people, and just critiqued, all the different options. And then we showed them the video of it unsticking from the sand. They said, okay, we want that one. Because driving into a crater, get a sample, easy. Anyone can drive down into a little crater and get a sample. It's the getting out. And while it's going into that crater, no Earth ephemeris, no COM, and it's out of the sun. So it's got 6 hours to go into the shadowed region, not really a crater, collect a sample, and then drive uphill to get back out. And the highest risk to the whole mission of the rover, once it lands, is get stuck. So they saw that and they said, okay, we believe this won't get stuck.
In fairness, it actually made the grade, meaning that it's on its way to space. That's one. And two, just looking at the videos, you miss the idea that when you're bolted down, it's belly bolting.
Yeah.
And when you got to get unbolted, just because you're unbolted doesn't mean you're not stuck to something. So the first move is to raise up. And when you go dead simple, you can't just push the up button.
Right.
And you miss that because it's a system. Right. And in this case, the system is integrated in, not added on in a stupid way.
Yeah, so we use those active suspension to get up off the launch locks. And if you're going to put all your money into that actuator to get up, it might as well be the actuator that you're going to use all day long. As opposed to Spirit and Opportunity, the best actuator on Spirit and Opportunity was used once. It was the highest torque. It was the only brushless motor on Spirit and Opportunity. It was used once to unfold the solar array. Click, and it's done. That was the biggest, most powerful actuator on the entire robot, and it was used once. And Curiosity and Perseverance had all these folding, weird mechanisms with other actuators that were required. This thing is fully assembled as it lands. There's no folding and unfolding, well, except for the mast. The mast does goes click. But other than that, everything else, it's no assembly required once it gets to the moon, which I think that's the simplicity argument, right? We had so much shroud height. Perseverance and Curiosity had this, a miracle landing system above the rover, right? And then they had a heat shield below that fell off. So they were sandwiched between the sky crane and an aero shield. So they had no room. So they had to tuck everything. And if you've seen the Apollo rover, it had to unfold out of like.
Those robots have an arm and other effectors. How can this robot have an arm and other effectors, or maybe the very right size?
Well, it could. It didn't. Oh, you mean the ball? Oh, I would love to put arms on this. It'd be right out of, science fiction to put arms on this. The Incredibles. So, but yeah, that's a payload. We're just being the ball right now. We'll be the arm on the ball later. But right now, it's just the ball. And it's nice to build a simple robot every now and then. Let me put it that way. and I kind of like it. Yeah.
Is there any more questions?
Is there?
What's the last question?
So robots that are being developed and researched often look like big hunks of just metal put together, but your robots are very stylish, and the gold and the white looks really nice. Did you have artists and designers on your team?
No way. I wouldn't trust one of my robots in the hands of an artist. It's too. Well, so let me just. Come on. Why? Well, the tan. That's another issue. All right, we got desert tan going, but why? White and gold? Yeah. Well, first, Reed Simmons was telling me about how it was important for the robots to kind of interact with people, and so many people are afraid of robots. It was just critical that everyone know that they're on the same team. So that's the colors. Those are the colors of the spacesuit. So everyone knows it's on the same team, right? But why is the spacesuit white and gold? Yeah. And any exposed metal, like aluminum, in the inner solar system, that's the right color because that's the color of our star. You know, if you go to the outer solar system, you'll go matte black because you want every photon that can hit you to keep you warm. But in the inner solar system, if you put raw aluminum out, it gets hot. So there's a reason your rovers have gold stuff, because that's the color of our star. Now, somewhere far, far away, there's a solar system with a blue star, and there's this great space program on one of their planets. And I think all their robots are blue and white. But you know, that's the color of our star. So I went into the anodized facility at JSC where they were making all these spacesuit parts, and I said, that's what I want. And you know, on every one of these, there was, well, we got schedule pressure. Can we not do anodized on this one, Rob? We got schedule pressure. I said, no. We're gonna do it. And on every one it was, well, we'd like to try something different. And I'd say, there's the door. You know, go find that other solar system that's blue. And I'm sure that.
It became a very powerful branding in addition to all those pragmatic things.
Well, the spacesuit is iconic. The spacesuit is so iconic. When you see it, it's just, and there are people now wanting to make the spacesuit green and all kinds of, I mean, I love green. What the heck are they thinking?
Lunar, like electronics, the lander, the robots, the gold has become a branding.
Oh my God, you know, you got that gold face on the spacesuit, you got all that Kapton on the LEM, the lunar rover had all that gold. Okay, I like green, but come on, that's just dumb. Just dumb. Go with it, and it takes discipline. Every one of those, you know, just to get through metal finish. Talking to my students, right? It takes a lot extra steps and time, but besides just the finish, you know, you gotta think it through. You're gonna make something. Why make it ugly? It costs just as much to CNC a rectangle as it does a curve, right? I mean, it takes the same amount of money.
You turn the clock back decades. At some point, all that mattered was that robots worked. Unfortunately, in the generation sitting in this room, they also have to look good. So, you know, get with it. And I'll tell you, if anybody here is given this kind of talk down the line in your own life, you know, you'd have a tough time going up against what we're looking at right now. But that is a testimonial to a body of life work and great leadership that you just don't trip on every damn day.
I'm not done.
You're not dead yet. Hell, we thought you were all walked. We thought this was your washed up talk.
Got a few more robots I need to build. Thank you, Howie.